Hey guys, how's everything going? This is JSer, who is not very good at algorithm, and I'm recording this video to prepare my interview from Facebook in June, which is exactly like 1 month from now. So actually, not that much time is left. So I'm trying to do as much practice as I can. And this video is about 1026 on LeetCode, maximum difference between node and ancestor. Let's take a look at the description first. Given the roots of a binary tree, we find the maximum value v, for which there exist different nodes a and b, where v equals the absolute value of the difference between the val, and a is an ancestor of b. Well, for the example here, so basically for every node on the same route, so on the same path, may generate a new value, right? A3, 5, 817, 363, 862, 871, 844, 2, something like this. So the maximum is 7. Well, for this binary tree, I think the first idea comes to my mind is that we can use recursion. So let's first analyze the basic form, like there is only a, 3, 10. Of course, for this case, there will be only two values, right? A, 3, 5, and A, 10, 2. Now, let's suppose we add a new node, like 1 here. What changes the situation? How the problem changes when a new node is added. So when 1 is added, it actually adds two possibilities of v value, right? One is 1 against 3, which is 2, and 1 is against 8, 7. So you see that the two values actually, if we know that the 3 is smaller than 8 and 3 is bigger than 1, actually we don't need to calculate calculate 1, 3, because it's definitely going to be smaller than 1 against 8, right? And of course, if 8 is like minus or something, and if here is like 5, 3 is smaller than 1, well, that might sound different. But the idea is saying, if actually for 1, we actually just pass it with the maximum, the largest number, and it will cover all the cases that the nodes bigger than 1. Suppose there's 5 or 7, it doesn't matter because 8 is the largest one. So we only check 8 with 1 with 8. And of course, it's another case that of the numbers smaller than the value. So besides the largest number, we actually can pass both the largest one and the smallest one. So that will cover all the cases, right? Yeah, so cool. We can use a recursion to do that. Okay, so the maximum, because it's absolute value, the max would be, we can set it to 0, to default to 0. Oh, so far, God. And then we can create a recursion method called node walk. The parameters first will be node, and next one is max and node max minimum, right? Okay, let's say we pass with max and minimum. If this, what we do? Of course, we just calculate the max, the two v's from max, min, and the current node's val, and update the result, right? Well, it's simple. So the result would be a result. Oh, if the node itself is null, we just return, right? Do nothing. And we update the result, means math max. The first is math abs, max minus node val. Next one is math abs, min minus node val. This is the result. Right? of course. And now we can start work on the children of this node. And the new max, I think. Okay, I can just use one-liner. Walk node left with max. Now the max would be max node val, right? Update the max, update the mean. Obviously, this will be called again on right node. So we cache it. New max equals this. New mean equals this. This is new max. New minimum. Okay, and now we walk from the root. Is the root might be empty? We're said that number of nodes in the tree is between 2, so it cannot be empty. We walk the root. What's the maximum? Max. Max itself, right? Because it's root, there will be no node, only ancestor. So the root would be val. The minimum? Yeah, itself. It doesn't matter. Okay, I think we're done here. Let's try to review our algorithm. Let's try to do it bug-free with one pass, okay? So for this kind of input, we'll first walk to 8 and the maximum itself, and the result would be, this will be 0, this will be also be 0, and the result will be, yeah, we find a bug, we need to update the max. And we find the new max, it's still itself, and the minimum, okay, it's still itself, and then we walk to the left. Left will be new 8, left with 3. Now we go to left node, maximum is 8, minus its 5, right? So minimum 5. Okay, so we updated result to 5, and the new max would be 8, minimum would be 3. So now we go to 1, and the maximum would be 8, minimum 3, so we update it to 7, the result. And the new max would be 8, the new minimum will be 1. Now we go to the null, right? Left node. But null is empty, so we return. Yeah, I think this would work. What? When it's not working. What? Really? It's not working? Like A3, it's just like this. Really? Wow. The input is this. I want to give up on engineering. Okay, we check A8, so yeah. Oh, allow me to update the result. Eight, 8. Why become so 10? Still, it's A8. Now we got here 14. We got 10. Maximum is 10. Minimum is 8. So we subtract the node val, and it become 10. Why? Node val is You see node val is less 2, right? So max, it should be Is it? This is not number? Node val. Type of node val? String? It's number. Uh-oh. So node val is 10, and max is 8, minimum is 8. The result would be max. This would be 2. This would be 2. This would be 8. So it's still 8. Oh yeah. Oh, there's no problem here. And we got 14. The max would be 10. And the minimum would be 8. So the result would be 10. Why? Max 4 and 6 and 8. So it should be, it's weird. Allow me to log. Is there something typo or something? Okay, so we got 4 and 6. Max is 10. Shit. God, sorry. This should work. Cool. At last I didn't do it bug-free. God. We're accepted, but not that fast. Let's analyze the time and space complexity here. For space, time, you see that each time we just traverse one node, so time is obviously n log n, big O n. Space, it seems that we don't use extra space, so it's constant. But there's a worst case of call stack, so worst case is big O n. Cool. Now let's try to improve it. I think there is nothing we can improve, right? The improvement is that we can reduce the space, because this is a typical. You see it's a typical tail recursion that we can rewrite it into iteration. Okay. Let's just try to iteration with BFS first. Okay. So as we did just now with the recursion, we need to pass on max min. So for BFS iteration, we need to push the node together with the min max and then handle them. For each round, we add a new null here, to the stack, to the queue, and as the ending identifier, and do that over and over again and update the result. So cool. Let's do it. Const queue equals. We just use an array here. While queue has elements, I need to put root in. Queue push root a null. Let head, while head equals queue shift. So for each round, so this means each round, use null as an ending identifier to do it round by. Oh, I think there's no need to do round. Yeah, there's no need to do the round problem because there's no information attached to the round, right? We just need to pass stack the max and the main, so it's already there. There's no need to do this. So I'll say let head, while head equals this. Forgot to push the max and min. Root val, root val. Const node max min equals root, right? Oh no, head. Just as what we did here, we'll update this. Copy the code here. Max node val, yeah, this is the same. New max is the same, and we just rather than walk, we push into the queue. This we push only if there is left. Head, sorry. Oh, node left. Of course, we do the same to if left node right. We push the node right. Cool. I think this will do. Try run the code. Yeah. This might be better. It seems that it doesn't help so much. Well, let's analyze the time complexity. For time, all the nodes will be traversed through only once, so it's linear time. Space, we used a queue to store the call stack, and the maximum is the half of the nodes, right? So it's 2. It's linear time. This doesn't change the time complexity, actually. Change the time or space complexity, actually. Well, for this problem, actually, we can rewrite it into iteration with DFS, right? DFS, iteration. For DFS, we will push to the end, and yeah, I'll use queue. Push them in and handle them and push them in. So it's a stack, okay, for DFS. So I'll create a stack root val as the min max. I'll define the method called push. So for the push method, not only we push to 3, push 3, we will continue push. Oh god, I'll remove the initialization. I push until all the left nodes are in the stack. While node stack push. Uh-oh. It's not possible. It's not possible here because okay, it's okay. I get it. Because I need to push the max and the main also in the stack. This method is not gonna work anymore. How can we do it? Well, I think the const push will be switch to not push the nodes, but push the node max minimum, right? Yeah, and then DFS, and then this way and this way. Yeah, cool. And actually we need the logic here. So the result will be we update it like this, okay? And then we will update it, and new max and new min is like this, right? And then if node left, if there is left node, we will continue push it. So we push node left, new max, new min. So when we push a node, actually there's no need to do the DFS check, right? Because we already checked the data, and there we don't need to undo. We check it back, check it over again. Well, anyway, just like the practice of do tree traversal, let's do it. Okay, so now we push the first one, right? Which is root val, root minimum. For the result, I think we don't need to do it now. We push this, and it means we need to, oh god, it's actually 2 o'clock in the morning, so my brain doesn't work very well. We will push the node and max and minimum. We push it and we create a new one and push all the left node into the stack, right? And we push the first one, and then we start popping, right? So while, let's say let top, while top we pop, whereas there is something in the stack, while stock, I'm creating actually a stock application. Okay, we pop the node, we will handle the result, right? Yeah. So actually this will be reused. This is the top, and then we can update the result. We separate the DFS into push phase and collect phase. This is the collect phase. So update it, and this should work. And then what we do, we will check, because it's already popped, we check if it has right node or not. If there's right node right, we will push node right. This is not very good. I need to calculate the min max again, right? first I'll copy the code like this. Node right, new max, new min. Left is handle, then we pop it. And like this, we pop it and then push the right in. It seems right, but it's not that elegant. New max, new min. Can we merge these two together? When we push in a node, if we keep track of this like a previous max and min, it might do, right? Okay, so actually this would be prev max, prev min. We push the node. For this case, the new max actually we stack push a node. Proof max, proof min. This works. And then now we could push right with directly. It's not okay. Wow, it works, I think. This is not actually a good solution, I think. Max is not defined. Oh. Stop. Max is not defined. 71. Here, there's no max. Not a number. Stack. We push all the nodes in, and then update it. Push it in. Oh, there is val here. My God. It's still not a number. We pushed it in. We get the top, and then we find the max. Val. We push node right in it. Sorry, I need to log top. Wow. Undefined. Stack is empty? What? We pushed the... Uh-oh. Ah, God. My bad. this top value undefined. Yeah. 0. Wow. So the first would be 3, 4, 3, 4, 6, 7. There's 1, right? There's no 1. Three, 4, 6, 7, 8, 10, 14, 13. Where's 1? 1 is gone. We push the root, and then if node left, we push the node left. Push. Oh God. Console log push node to val. We push 8, then push 3, we push 6. There's no 1? We should push 1, right? Node left. Left is node left. We push 8, left is 3, and then we push God. Wow, I think I need to go to sleep, so sorry for my mistakes, guys. Okay, for this case, so actually for DFS, it doesn't change that much for this problem. And we will do a follow-up on tree traversal, everything in the future videos. Hope you will please stay tuned. And I hope there will be some good news to tell you guys in June's interview. And okay, so that's all for this problem. Hope see you next time. Bye-bye.